Welcome back to the workshop. I'd like to take a look at our two large theorems for the second section, really one large theorem and one small theorem, but the two theorems of our section here. So let's go to our notes. So very large theorem is our first one. So let's say that we have a universal set U, and let's say that A, B, and C are subsets of U. Then we have each of the following things are true. All right, so A union B is equal to B union A. Doesn't matter what order I union things in, they're the same thing. Same thing with intersection. So to say that things belong in A or B is the same as to say that things belong in B or A. To say that things belong in A and B is the same thing as saying things belong in B and A. Okay. So this is symmetry. We'll see a little bit about symmetry later, but we can flip it. That's what we want to say there. Yes, okay. All right, so here, what we can do is we can, when we're taking a look at unions only, we can group them however we like. So we have A union B, and then union C is the same thing as A unioned with B union C. And then if we were to do the intersection of A and B first, that's the same thing as taking the intersection of B and C first. This is saying that there is associativity. So associativity in unions and intersections. We also have some distributive laws or rules, whatever you'd like to call them, and we can distribute the union over the intersection. So we can say that this is A union B intersected with, right? So we distribute the union to B, and then we distribute the union to C. So A union C. And then we can also distribute the intersection over a union to say that we have A intersect B unioned with A intersect C. So I can distribute the union over an intersection, or I can distribute the intersection over a union. And this is a distributive property. All right, so if I take a set, right, this is where we use the universal set and where we're talking about the complements. If I take the complement of a set and I take the complement of the complement, it's actually going to give me back my original set. All right, A complement is everything that's not in A. So if I take everything in A and put with it everything that's not in A, I would have everything, right? Because everything is either in A or it's not in A. So when I union those two sets, I get everything back. All right, now if I take things that are in A and I take things that are not in A, what things are in common, right? If I were to take the intersection of things that are in A and things that are not in A, right? Of course, that would be empty. There's nothing in common because that splits everything into two subsets, right? I can take the universal set and I can say everything is either in A or it is not in A. Those two things are separate from one another, so their intersection is empty. All right, so this one, A is a subset of what? Well, A is a subset of A union B, and B is also a subset of that. B is a subset of A union B. And the intersection of A and B is a subset of A, and the intersection of A and B is a subset of B as well. And then if we were to consider complements instead of set subtraction, complements work within a universal set, whereas the difference of two sets works outside of the idea of a universal set. But if we were to if we wanted to, working within a universal set, we could express a difference as an intersection. Okay, A minus B is simply A intersected with the complement of B. So when I look at the complement of B, I'm looking at everything that's not in B. So I take the elements of A that are not in B, and that gives me the difference here. All right. So that was a long list of things. What follows are two that are very similar to what we just looked at, but these two are called DeMorgan's laws. So we're still working with subsets A and B and universal set U. And with that, we have the following. Okay, we have A union B, and if we were to take the complement of that, that is actually the intersection of A complement and B complement. Interesting. Similarly, if I were to take the intersection of A and B and the complement of that, what I end up with is the union of the complements. And those are DeMorgan's laws. In our next video, we're going to take a look at Venn diagrams, as well as just some examples. We'll use our Venn diagrams to help. And I believe that we'll take a look at, I was thinking we'd look at DeMorgan's laws, but it looks like maybe we won't. It's probably a homework assignment then to use Venn diagrams to show that DeMorgan's laws hold, or show the equality holds. But that's all for now. We'll take a look at those examples in our next video, and then we will have one additional video beyond that with just one more definition and example. So the next video may be a little bit longer, and then one more short video at the end. So thank you for now. I'll see you guys shortly again here in the workshop.